In this video, we will introduce the concept of center of mass, which you already have seen in 2305, so this will be a review of sorts. Now, we won't really have true use of center of mass until much later in the course, but we can use it to rewrite conservation of momentum in a convenient way, so that's why I'm introducing it now. So let's say that we have a collection of particles, like so, and they're all given labels like 1, 2, 3, I until n, which is the total number of particles, like that. Each of the particles, of course, has then a position vector associated with it. So, for instance, the ith particle will have a position vector like this, which is r sub I, with respect to some frame that we've defined here. The center of mass then is defined as follows. Center of mass, it's the average position, and I'm going to use capital R2 to indicate the center of mass. The center of mass is the average position of all the particles weighted with their masses. Right? So each particle has a position, but it also, of course, has a mass. So if I want to write down the center of mass, then it becomes 1 over m, capital M here, that's the total mass, times the sum, where alpha goes from 1 to n, it's the total number of particles, of then m alpha, and then the positions of the alphth particle. So we can write that as m1 r1 plus m2 r2, like that, divided by the total mass, which we could also write as m1 plus m2, etc., until mn. And that's the total mass, like I said. Okay. So this is for any number of particles. If we specifically look at a two-particle system, so let's have a two-particle system here, which is only one particle here, and particle 2 there. Then we get, obviously, that R equals m1 r1 plus m2 r2 divided by m1 plus m2. So we can see, and this will actually be done in a homework, that the center of mass, so let's do this explicitly. Oops. Center of mass would be there. And we can see that it actually lies on the line that connects the two particles. R1 and R2. And it also lies closest to the heaviest particle. Okay. The other important case to consider is if all masses are the same. So that means that m1 equals m2 equals all the other masses, and that just equals m, which gives us the total mass, capital M, is just n times m. Under those circumstances, we can just see from this formula here, all the m's will cancel out, and all we get is that the center of mass is just equal to 1 over n times the sum of alpha goes from 1 to n of R sub n. Or if you want to write it without the sum, it gets to have this form. So it's a little bit easier to calculate than it really is the average position of all the particles. Now let's go back and look at the total momentum of this system. So all these particles could in principle be moving with some velocity, and that means that each of them has some momentum. Let's look at the total momentum of the particles. So we have that the total momentum of the system, P, is given by the sum over all the particles, like so. So if you write that out explicitly, that becomes sum from alpha goes to 1 to n of m alpha r alpha dot. Now if you compare this here, just scroll back up here. If you compare this to the expression for the center of mass, you can see that they're almost the same. The only thing that differs is that this has now got a time derivative there, and this is then has this normalization constant of the total mass. So this is therefore equal to capital M, the total mass of the system, times the velocity of the center of mass. From this we can see, in other words, that the center of mass moves as if the system consisted of one single particle of mass capital M located at the center of mass position, subject only to the external forces that acting on the system. Right? Because we just showed and earlier that P dot equals only the external forces, which means that this then has to equal to capital M times capital R double dot. Okay, so to summarize this then, so the center of mass of the system moves as if it consisted only of a single mass located at the center of mass and subject only to the external forces on the system, none of the internal ones. That's a rather convenient way to look at it, because that makes it possible to separate the movement of the system as a whole, which is given by the center of mass coordinates, like capital R and capital P, from the internal movement of the particles within the system. And that's a justification for treating objects as if they consisted just of a point whose mass equals the mass of the total system. Okay, so when we're doing physics, often we will use a point particle to symbolize an extended object, and this motivates why it's okay to do so. All right, so let's now extend this concept of the center of mass to a continuous system. So let's copy this. So for a continuous system, that is a mass like this, we can divide it into pieces, where each piece, like this piece for instance, will be the alpha's piece. It has some mass m alpha and some position r alpha, and that varies continuously within the object. We can take this and just generalize it to an object that's being divided into smaller and smaller pieces. And when we do that, you should know that the effect of that is to take the sum and turning it into an integral. Right. So for a continuous system, R is going to be equal to 1 over m times the integral over the position over the object, integrating over the mass. Okay. Now, integrating over the mass is perhaps not the most convenient thing you can do. It's easier to integrate over space, but we know that each of these pieces, each of these little pieces of the mass, have the property that their mass equals the density times their volume. So this becomes 1 over m becomes the triple integral of r times rho dv, like that. Okay. Now, if rho is constant, if we have an object that has a constant density, that means we can take rho outside of the integral. Then we can get rho over m. We know that rho is the total mass divided by the volume. So rho over m then just becomes equal to the total, to 1 over the volume. So the center of mass expression for a continuous object with constant density is 1 over v times the integral of r dv, which is of course the same thing as the y dx dz. Like that. So next, let's apply this to a specific example, and that is that of a hemisphere, center of mass of a hemisphere. Now, one of the advantages of doing things this way is that you can prepare things in advance. Try doing this on a blackboard; it's not going to work. So this is anyway a hemisphere. This is seen with the xz plane head on. You have to imagine that this object is symmetric around the z-axis, so that it's really a hemisphere, not just a half disk. We're going to say that this has the radius r, so that this is coordinate plus x in the x direction, and over here we have minus x. Okay, and in order to make this work, we have to apply now this formula here. So you want to figure out where is the center of mass. Now, just from symmetry, we can say that it has to be on the x-axis, on the z-axis, clearly. But the question is exactly where on the z-axis. So because of that, we can say that by symmetry, the x and y coordinates of the center of mass are 0, and z, therefore, is going to be equal to 1 over v times the integral in 3 dimensions of z dx dy dz. And we'll rewrite this as 1 over v, and here we have dx dy, and then z dz. This quantity here within the parentheses is the area of a section at height z, section of the hemisphere at height c. Here's that the section. So this here is z. We'll take the thickness of this section to be dz. Okay. This section has some radius r. That's this radius here, and we know just from Pythagoras' theorem, this distance there is of course capital R, that capital R squared is z squared plus little r squared, or in other words that r squared is capital R squared minus z squared. This means that the area, which is pi little r squared, is actually going to be equal to pi times capital R squared minus Z squared. So that's A. The volume of a hemisphere is obviously going to be half the volume of a sphere. So that's 2 pi thirds capital R cubed. So now we have everything that we need to calculate this. So we find that Z is equal to 1 of the volume. We won't put that in quite yet. So this is the area here, same as this quantity here, times Z dz. And we have to integrate now Z from 0 to R. Those are all the possible values that Z can take. And then we'll plug in the expression for the volume. So that's the final answer. Z equals 3/8 capital R. Whenever you solve a problem, you should make it a habit to check if that's reasonable or not. And we can see that this is a reasonable value, because imagine that instead of a hemisphere, we had a cylinder. So the cylinder seen from side on would look something like this, right? It would have height R and radius R. By symmetry, its center of mass should be at the center. So for the cylinder, the center of mass is going to end up at Z equals R over 2. For the hemisphere, which is fatter near the bottom, the center of mass should be lower. 3/8 is less than 1/2, so that makes sense. In the book, they also calculate the center of mass for a cone. It has even more of its mass near the base, and there we found that for the cone, Z is in fact 1/4 times R, which is then less than Z for the hemisphere. So that's a reasonable value. This kind of calculation we'll use later in the course to a greater extent. I will give you a homework problem right now to calculate one of these, but the greater use for this will be later in the course.